As promised, we are going to talk about weighted least squares. So let me first give you some intuition as to what do I mean by weighted least squares. Well, let's go back to least squares. A bunch of data points, and I want to fit a model to it, a line. The line is parameterized by y is equal to m, slope, times x, plus b, the intercept. And least squares said, formulate the estimation of m and b as minimizing this error function that minimizes the square of the sum of all the vertical distances between the point and the underlying model. Good. Now notice that in this estimation, all the data points are equal. Everybody factors in to the estimation. Their vertical distance matters just as much as anybody else's vertical distance. Fine, nothing wrong with that, perfectly reasonable way to do things. But you might imagine that some of your data points might be more meaningful to you than others. Why? Well, let's imagine, for example, that these are readings from some sensor, and you happen to know that these sensors are more reliable than these. Well, maybe you want to weight these more because you trust the underlying measurements more. Or let's say that you just know that you're going to have more data sort of near the origin here with small values of x, and you're not going to have a lot of data out here, so you really want the line to fit well here, and you care less what's happening up here. You might put more weight on that. And in this example, for example, if I had said these two data points matter more than these four data points, well, maybe the line should look more like this, so I'm really minimizing those vertical distances. I'm taking a big hit over here. Look at these errors, but you know, I don't really care what happens out here because it's rare that I'm going to get any data there, and even if I do, I don't really care about it. This is sort of where I live. So you can imagine a world where you care more about certain data points than other data points. Now, that's up to you to decide. You, the person generating this, the same person generating x and y, has to tell me what data matters. Weighted least squares can't tell you. All I can tell you is once you have told me what's important, I'm going to estimate the model parameters for you. So here's what we're going to do. Quadratic error function is here, sum of the squares of all the vertical distances. And now all I'm going to do is exactly what I promised. I'm going to weight each error. Notice that this is inside of the square. I'm going to weight each error by some scalar value. Notice that wi is indexed on your summation. Why? Because every data point, xi, yi, has a weight associated with it, and that weight is going to determine how much do I care about this. And what's the intuition here? This is some vertical distance. And if I multiply that by a value greater than 1, what am I doing? I'm saying, ooh, that error is more meaningful, and since we're trying to minimize the error, that point will be more important. Or if that value is less than 1, it may say, well, sure, it's a high value, but I'm going to squash it, and so it will contribute less to the overall error. Okay, so that's the intuition for what that weight is going to do right there. So let me rewrite that a little bit. Let me remind you that mxi plus b minus yi we've been writing as delta I. That's the vertical distance. And what we've been doing, ignore the w for a second, is just summing up the square of all those deltas. And now I'm going to just, as I promised, multiply that error by some weight wi. Notice again, both are being indexed on that parameter there. And then again, I'm going to square that, sum it, and then hopefully I can minimize that in a simple way. Okay. So by way of intuition, let's unpack the summation for these 6 data points right here. W1 delta 1 squared plus W2 delta 2 squared plus so on and so forth up to W6 delta 6 squared. Okay. Now imagine we go back to here and I say, you know, these 2 data points are where I live. I actually don't even care about these data points. So let's go ahead and just set W1 and W2 in this error up here to 1. And let's set W3 through W6 to 0. Now that's sort of a weird and somewhat extreme thing to do because if I'm setting these weights to 0, I may as well ignore the data points. Don't even put them in the system. But just to give you some intuition, what's going to happen here is that as I'm computing this error, W3, W4, W5, W6, those errors go to 0. So no matter what I change in M and B, those data points are irrelevant to me. Don't care if they have small error, big error. And so what's going to happen is your whole world are those 2 data points, and you're going to fit a line exactly through them because a line goes exactly through, with a slope and intercept, goes exactly through 2 points. Now again, this is an extreme version, but you can imagine softening it. You can imagine saying, well, this is maybe 0.9 and this is 0.1. So I care a little bit about what happens here, but not that much. Or you can imagine they're all 1, in which case I'm back to a least squares estimation, and there it is. Weighted least squares is just a generalization of least squares where you say, I'm indiscriminate about the data points. And weighted least squares, you say, I have a preference to weight certain data points over other data points. All right, let's see how to formulate this. All right, let's go back to least squares again. We've got the sum of the square of the vertical distances where the model parameters are m and b. There's my model parameters m and b now in our linear algebraic formulation. Of course, I've got the column of x's, the column of 1's, and the column of y's here. And let me just remind you that, of course, that this is mx plus b minus y, which is just what you see there. A little bit of notation. This is the matrix X. This is the vector U. This is the vector Y with all the Y components, and we've been calling that vector the vector delta. I haven't done this yet. I just have a vector of a bunch of the vertical distances that I want to square and then to sum. So the way I do that is I take the vector norm, that is the square root of the square of the components, and then I square that to get rid of the square root, which then gives me exactly that quadratic error function. So now I have my quadratic error function that we've seen before, E of U. U, of course, is my unknown MB. It's the vector norm of the differences, quantity squared. And now we know how to, we can turn the crank on this. We know how to minimize that. But now let's go ahead and do the weighted least squares error function. So what I'm going to do is I'm going to take that quadratic error function right there, and I'm going to drop in a weighting matrix. So big W is this weighting matrix. What is the weighting matrix? It is a diagonal matrix, which just means it's 0 everywhere except on the diagonal, which by definition now means that it is square. So what's on the diagonal? W1, W2 up to Wn. It is the weight associated with each data point. Okay, so if it's 1, 1, and then a whole bunch of zeros, that's a perfectly fine diagonal weighting matrix. And what am I doing here? I'm putting it inside the vector norm multiplying the delta vector, xu minus y. Well, let's make sure that actually makes sense to us. So first of all, what is xu minus y? It's right here. It's delta. So this is just a vector of deltas. And now I have a matrix multiplying that. I'm going to get what? N by n by 1, n by 1. So this is going to give me another vector. We'll see what that is in a second. And then I'm going to take the norm of that and then square that. Okay? And it better be this. So let's make sure. Well, first row of the matrix times this is what? W1 times delta 1. And then everything else gets a 0. Second row, W2 times delta 2. Everything else is 0. And of course, the last one is Wn times delta n. And notice that's exactly what I want. So inside the vector norm, inside the squaring, I now have W1 delta 1, W2 delta 2, W3 delta 3 up to Wn delta n in a single vector. This is a diagonal matrix times a vector. That gives me a vector. Now I have the weighted errors in a vector. And now I can take the vector norm and square, and that's what that is doing right there. So all I had to do this weighted least squares is toss in that little weighting matrix right there. All right, so that looks good. So the good news is that the weighted quadratic error function and the unweighted quadratic error function look pretty similar. I'm just lugging around a new matrix here. Now the question we just have to ask ourselves is, well, how hard is this to minimize? Can we do the same trick where we differentiate this, set equal to 0, and solve? Well, first of all, that's clearly still a paraboloid because there's nothing different here. It's just a different vector. So this is still a paraboloid. So we still have the hope that we can differentiate set equal to 0. We just got to make sure we can actually do that. So when we come back, we're going to take that now weighted quadratic error function and turn that crank of differentiating, setting equal to 0, and hopefully solving, and we'll see what the solution looks like. All right, we'll see you in a few minutes.